Now that we've finished our analysis of different forces that are involved in fluids, we're going to turn our attention to what is really the more exciting part of fluid mechanics. And so we're going to move away from fluid statics, where the fluid was at rest and not in motion, and now add that motion back in and talk about fluid dynamics. And so in this section, we're going to skip chapter 3 in your book and move straight to chapter 4. And the reason for that is that chapter 3 talks about pressure variation in fluids in motion, and it seemed logical to me, and it'll make sense later, that we put fluids in motion in context first, understand how we calculate things like conservation in mass for fluids in motion, and then go back and consider the pressure variation in fluids in motion. And so we'll go back to chapter 3 a little bit later in the semester. But for now, we're going to skip it to chapter 4 and talk about fluids in motion in particular. So the first thing we want to do when we have a fluid in motion, in any sort of dynamics, we need to define a coordinate system and a reference time. Okay? So to explain that, I want to consider a fluid particle P, where the location of P is denoted by a position vector in a fixed coordinate system. And what I've done here is I have a Cartesian coordinate, a three-dimensional Cartesian coordinate grid, where we have the x-axis pointing into and out of the board, the y-axis aligned with the board, and the z-axis vertical. And I've given each of those a unit normal vector, I hat, j hat, or k hat. And this is normal notation, that I hat is just a unit normal vector in the x direction, j hat is similar for the y, and then k hat's a unit normal vector for the vertical. Okay, and so if we have a particle P that's out here like this, there's some vector that defines its position that goes back to the origin like this. So here's P, and that tells us the location of P at a particular time. And so you'll see me use vector notation a lot in the class. And so if we define that vector as R, it's a vector R of P, so that's a location of P. And we can write mathematically that R sub P, and it's a vector, is equal to x sub P T at I hat plus y sub P T at j hat plus z sub P at T k hat. Okay, so that's just vector notation with the tilde underneath the variable there. It just tells you that it's a vector, and in this case this vector has 3 components, and those 3 components are the 3 orthogonal dimensions that we're using, x, y, and z, sorry. Okay, and we can write that more simply in vector notation as just bracket x p of t, yp of t, and zp of t. Okay? And once we define that position vector, it's pretty straightforward to define our velocity vector, okay? And the velocity vector, if you recall from your physics and your dynamics class, is simply the time derivative of the position, okay? So we can write that out as a velocity v. We'll put a tilde under it because it's a vector. V of p is equal to d over dt of r tilde p. Okay? And then we can write that out. We have dx sub p over dt I hat plus dyp over dt j hat plus dz over dt k hat. Okay, and that defines our velocity vector. We actually replace the dx, dy, dz, dt's by a variable because we use them so commonly in fluid mechanics. So we can write that a little bit shorter notation, and the velocity vector becomes u, which is the velocity in the x direction, I hat, plus v, the velocity in the y direction, j hat, plus w, the velocity in the z direction, k hat. And this here defines our velocity vector. Okay? And that velocity vector has a magnitude and a direction. And just like with any other vector, we can calculate that magnitude or the direction if we know the three components. Okay? The next logical thing that we'd want to consider, you might expect, would be the acceleration. But that's a little bit more complicated in fluid mechanics than some of the stuff you did in dynamics. And so we're going to go over a few other details first before we go back and look at the acceleration of a fluid. Okay? The first thing we want to consider is how we're going to define the reference frame. And there's two ways we'd commonly do that in fluid mechanics. The first one is a Lagrangian reference frame, and that's named for Lagrange, the scientist who first defined it. And that's a reference frame that moves with the particle motion. So if you have a particle here and it moves like this, you're going to define the position and the velocity of that particle at each point in time, and you're going to move with the flow. So basically the thing you want to remember for Lagrangian situations is that your reference frame is going to move with the flow. And this is very useful if you're looking at a finite number of particles of, say, coal being injected into a combustion plant or drifters in the ocean. If you're doing a study of ocean circulation dynamics, we often use drifters where we put them in the water and let them drift for several months to see where they go. And in that case, you really are using a Lagrangian reference frame to analyze the fluid dynamics. But often it's very cumbersome to do it this way. And so what we do instead is we look at it, use the other reference frame, which is more common in probably all the problems you'll do in this class, and if not throughout your undergraduate career, will be based on an Eulerian reference frame, which is named after Euler, who also first defined that reference frame. And it considers the motion at a particular point regardless of which particle is there. So now I'm going to look at this one point, and I'm going to look at this point no matter what goes on, and just look at how the velocity changes at this point, or the fluid properties change at this point while I look at it. Okay? So what we're going to do is we're going to define a grid and look at that particular point here, and as the air flows past this point, we're going to define the velocity through time. Instead of tracking the position and velocity of each particle, we're going to watch that velocity vector field at a fixed point. And when we do that, we can write that out mathematically as v tilde equals v tilde, and it's a function of x, y, z. That's the point that we're looking at, and then a function through time. And as I mentioned before, almost all of the fluid mechanics problems that we'll look at, and most of everything that's done today, is done from an Eulerian perspective. And even if we do have data that's collected in a Lagrangian perspective, we often translate it into an Eulerian perspective in order to really understand it. But that's our basic intro for fluids in motion. Next, we're going to talk a little bit about a few ways we can visualize flow, because it is difficult to do. Air you can't see, you have to add a tracer. And water can be a little difficult as well, especially if you're in the water swimming. It's very difficult to observe the flow of the water. So we'll talk a little bit of ways we can graphically visualize what a flow is doing in the next video.